Good evening and welcome to lecture number 19 for MT225. Tonight we are working on frame problems. We introduced frames on Monday night and we'll be practicing on a couple more of those tonight. Let's see on our administrative details here. We have homework number 8 has been posted. That is a bonus homework assignment since next Wednesday we'll be doing our exam on structural analysis. So method of joints, method of sections, and frames. This is a homework assignment centered around frames. So doing it will give you good and valuable practice at getting frames down for the exams. Frames are gained for the exam, but it's not required that you turn that one in. If you turn it in and you get a better grade on it than one of your previously submitted or future submitted homework assignments, this grade will replace it. Homework 7 is due tonight, and I'll open up the floor for questions on that one in a moment. And quiz number 6, I don't think I put it in here, but quiz number 5 has been returned. That was on homework 6. So if you submitted something for that, I returned that to you yesterday. And quiz number 6 is on homework 7. That's method of sections. So that will be released sometime Sunday and due midnight Monday. Let's see here. And exam 2 on the 14th, 5 p.m. at the hangar. Sample exam 2 is online. So that is one of the previous year's exam 2s. And chances are Monday night next week, if nobody comes in with specific problems that they want me to solve and to go over, I'll probably just go through and work out exam 2. The exam 2 that I've put online. I'm gonna have to verify. I should have the solutions up there for the old exam 2. I'll check that tonight. If I don't, I'll put the solutions up there too, so you have something to check against. But I'll probably work through those problems at the very least on Monday night as a review of method of joints, method of sections, and frames. But if you have other questions, come in with them. I'll be glad to answer those. But that'll be my fallback. Let's see. So homework questions. The gentlemen online tonight have suggested problem 3 on the homework to take a look at. So that sounds like a plan to me. So let's take a look at problem number 3 on the homework. Problem number 3 is that one right there. So here we've got a relatively complex truss, one that would be would be solvable by method of joints, but would be something that would take a long time to do. We'd have lots and lots of joints. There are lots of members here. We have let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 members in this thing. But fortunately, the problem says to use method of sections, determine the force and state of tension or compression in members CD, CH, and HI. Or CD, CH, and DH. So let's draw that out first here. We've got 4 bays at 10 feet apiece. So each bay, so the whole length of the truss is 40 feet. We've got a pinned support at A. We've got a roller at F. And we've got, let's see, 1, 2, 3, 4 bays. And we've got something that looks like that. So we're going to midpoints. There we are. And we've got our cross members. So not quite as pretty as the drawing on the homework, but it'll do for our purposes here. We've got a 6 kip load at D. We've got an 8 kip load at E. We've got a 10 kip load hanging in the middle at H. And we've got some geometry. We've got 9 feet for our height and 4 bays at 10 feet each. And let's see, A, B, C, D, E, F, G, All right, so let's go over to the camera. There's the drawing I've got. Now, we are looking for members CD, CH, and HI. And unfortunately, there's no way to cut through the truss so that we only get those three members. If we ended up trying to come up with some sort of cutting plane that cuts through those, we'd end up with something that that wouldn't really work all that well. Really wouldn't give us any useful information, too many unknowns to really work with. We could cut through like this. That would get us CD, DH, and GH would come for free. Even though we don't really want it, we'd end up getting it in part of our solution. Then we'd have to figure out how to get CH. Similarly, if we cut through like that, we'd get CD, we'd get CH, and we'd get HI. We really don't want HI, but it would come in for free. So the strategy for solving this problem to get the three members that we want, if we were restricted to using method of sections, and I suppose reading the problem here, it does say using method of sections, find those members. But if the problem was a little less restrictive, we could use method of sections to get two of these, and then we could do method of joints. Jump to H, for example. With knowing what we know up here, we'd have two unknowns and we'd be able to solve for the one we need. So that's one strategy, but another would be to do one cut, get two, do another cut, and that would get you the remaining one. You can stack cuts of the truss and do them in sequence. So let's first solve the external problem. We'll get set up here and we'll do our first cut. So let's see here. In our free body diagram, I'm just going to draw on top of this here. We'd need a reaction at A, so we'd need RAX and RAY at the pin. At the roller, we'd have RFY. Coordinate system to the right and up are positive, counterclockwise moments are negative. By the way, while I'm thinking about it with respect to the exam, I'm sure I'm going to say this again, but you're allowed to have two reference cards, two 4-inch by 6-inch cards, both sides, whatever you want to put on them. So the procedures for method of joints, method of sections, example problems, fully worked out, anything you want on those. So that gives you a lot of freedom for reference there. So this is a non-concurrent force problem. So we'll do our sum of forces in the x direction, sum of forces in the y direction, and sum of moments about a point. So sum of forces in the x direction, all we've really got is RAX. No other side forces here, so RAX is 0. So no RAX. Might have been able to predict that, but no matter how you do it, you got to state something about it, because that's worth points in the problem. And it's worth it to realize in the whole structure that this pin could be replaced by a roller because it doesn't need to handle any side forces. So don't just ignore it and don't say anything about RAX. Whether you let the math tell you or you let your insight into the system tell you, either way works, but you have to say something about it. So RAX is 0. Sum of forces in the y direction, we've got a positive RAY, we've got a positive RFY, then we've got -10, -6, and -8. So -10, -6, -8. And then we need moments about a point, and may as well pick point A. So RAY will not have a moment, but the 10 kip force will, RFY will, and the 8 and the 6. So we're going to have 4 terms in our moment equation. We got to be careful. One of the mistakes I saw on the quiz was people forgetting the arms, just writing a force in instead of the force times the distance. So be careful. Make sure you don't forget your arm. Every term needs to be an arm times a force. So this 10 kip force, for example, is 2 bays away, and that is 20 feet, since each bay is 10 feet. So we have 20 times 10, 200 kip feet. If we're pinning at A and pushing down at H, that's a clockwise moment, so that's negative. RFY is 40 feet away, so it's 40 RFY, and that would be a counterclockwise moment, so it's positive. The 6 kip force and the 8 kip force, we'd have to do a little bit of assuming here that this is a relatively symmetric structure. We really don't have anything in the problem that explicitly tells us that. This could be offset just a little bit to one side or another, so we wouldn't necessarily be able to see it, but we're down to whether we either make the assumption that each one of these triangles is essentially equilateral, so that we have a straight line coming down through here, not equilateral, but at least it's isosceles, that we've got a straight line coming down through here that would give us equal sides. We can't do the problem if we don't assume that. So essentially we have to assume that these two angles are the same. There's no way to do the problem otherwise, and that will put the joints up here halfway in between the joints down here, so we can make measurements to it. That's an assumption. It's a reasonable assumption. It doesn't trivialize the problem, but it lets us solve it. So it's a reasonable assumption to make, and we have no other better information from the problem that would tell us otherwise. So we'll have to make that assumption. That means that the 6 kip force is 10, 20, 25 feet away. So it's 25 times 6, that would be 150. Pushing down, pinned at A, clockwise, so negative. And then the 8 kip force is 10, 20, 30, 35 feet away. So we'll have 35 times 8, that's 70 times 4, 280. So minus 280. So there we've got our 4 terms in our moment equation. If we clean the moment equation up a little bit and combine all these, we've got 20, 150, and 280. 200, 150, and 280. So this says that 40 RFY minus 630 equals 0. And if we solve that by adding the 630 to both sides and dividing by 40, RFY is 15.75 kips. Came out positive, so we know our direction's good. 15.75 kips. We can look at the structure and ask if that's reasonable. Well, we have this 10 kips right in the middle, so we'd expect a 5 kip and a 5 kip split. But then we've got all this extra stuff over here. And a lot of that is closer to F than it is to A. So it's going to drive up A's load by quite a bit, by another 10 3/4 kips. So RFY, 15.75 kips. And now we can go to our y direction equation and replace RFY with 15.75. So RAY plus whatever this number comes out to be has to be 0. Well, 15.75 minus 10 minus 6 minus 8 is negative 8.25. So RAY is 8.25 kips. So those are our reactions. They look pretty reasonable. The sizes are reasonable. The distribution looks good. So we have a chance of being right. So to move on, we've got to do method of sections. And because otherwise we're stuck doing method of joints, and we'd have to kind of march across the truss, maybe working A, then B, then maybe I or C to try to get, in fact, we'd have to do I, then C, and that would get us at least 2 of the members, but that's a lot of extra work. We don't really care about what's going on in anything except CD, CH, and DH. So our table for our final answers should be looking something like loading kips, tension and compression. We should only have 3 members in that row. In that table, we'll have members CH, we'll have CD, and DH. So just 3 of those. So a bunch of them we don't really care about. Well, we can do a cut one of 2 ways to net 2 members. And I'm going to go this way, just simply because it involves the fewest number of external forces. If I cut this way and I close to the left, I'm going to have to deal with this 10 kip force. And that's just another force that I'm going to end up dealing with. If I cut this way and close to the left, really the only external force is RAY. So I get a much simpler looking truss. So I'm going to close to the left and do my cut like that. So the piece of the truss that I'm going to keep, and I'll grab another sheet to go to on that. I'll draw the piece of the truss I'm going to keep. So first I draw the members that are completely contained in the truss. So that's this triangle ABI. Then I've got BC and CI. And then I've got the members I've cut through. CD, I've got this little stub for CH, and this little one for HI. So that's where my surface is cut through and opened up the forces, exposed the forces that are in those members. We've got a force here of 8.25 kips. That's an A, B, C, and I. So where we've cut through, we've got a force due to member or force felt by member, CD. We've got a force felt by member, CH, and a force felt by member, HI. So those 3 forces are the forces the piece of the truss I'm keeping feels from the piece of the truss that I'm throwing away. So the principle is if I can throw away this part of the truss, but at that same instant that I throw it away, I exactly apply the forces that the rest of the truss used to be applying, nothing will change in the part of the truss that I'm keeping. So we've got that. We've got the geometry from the problem. So we've got a non-concurrent force problem. So we have our sum of forces in the x direction, sum of forces in the y direction, and sum of moments about a point. We are going to need an angle. We're going to need that angle right there. And that angle we can get from over here, which because of parallel lines and all that, we've got the same angle here. And because of our assumption that these triangles are symmetric, that'd be the same as that angle there. So any of the angles that we get to horizontal are going to be exactly the same. So we can get that any way we want. One way we could do it is just by finding the angle in that triangle. This is 9 feet high. Each bay is 10 feet, so this would be 5 feet. So we'd find the inverse tangent of 9 over 5. And that'd give us 60.945 degrees. So 60.945 degrees. So that'll be the same here, 60.945 degrees. So there we've got everything we need to be able to figure out the equilibrium. So let's try it out. Sum of forces in the x direction. We have all of FHI to the right, so it's positive. We have all of FCD also to the right and positive. Then we're going to have a piece of FCH. We're going to have the adjacent piece of FCH, and adjacent goes with cosine. So we have cosine of 60.945 degrees. And no other forces in the x direction. So that's our x direction sum. In the y direction, we have all of 8.25 kips up, so that's positive. And then we have a piece of FCH down. So FCH down, that would be the opposite side. Opposite side goes with sine. So we have FCH sine of 60.945 degrees, and that's down, so it's negative. Nothing else in the y direction. So that equation is looking promising. And then we've got to do a moment equation. In the moment equation, we've got to pick a pivot point. And this is the critical step. This is where we can make or break the problem, picking the pivot point for our moment equation. We want to make sure we knock out the most number of unknowns that we can. And generally, if you look at where the lines of action of the most number of unknowns intersect, that'll be the point to pick as your pivot point. So A would be problematic here because although it would knock out HI, we're going to have kind of complex moments, especially for FCH, and we'll certainly end up with two unknowns. Same with I. C, however, is looking like a good point to go with because if we pick C, we'll knock out FCD and FCH. We'll have a reasonably easy moment to figure out from FHI, and then a reasonably easy moment to get from the 8.25 kips. So not too bad. And certainly only one unknown in our moment equation. And that's what we always want to see. So we'll take our moments about joint C. So that means no FCH, no FCD. We will have a moment from FHI and a moment from the 8.25 kips. So we need an arm for HI. Well, remember the arm is the distance between the line of action and the pivot point. Well, the pivot point is 9 feet away from FHI. So we have 9 FHI. If we pin at C and pull to the right at H, that will be a counterclockwise moment, and counterclockwise moments are positive. So we have a positive 9 FHI. So we can draw the coordinate system in to be clear there. We have X and Y and counterclockwise moment. Then we have the 8.25 kips. Well, the line of action for that 8.25 kips goes up like that. So we need to measure over to C. Well, we've got 5 feet plus another 10 feet. So it's 15 feet away. So we have 15 feet times 8.25 kips. And that gives us 123.75. If we're pinned at C and pushing up at A, that would be a clockwise moment. So it's negative. And there we go. There are equations of equilibrium. 2 of them we can solve right away. The other we'll have to plug some things in to solve. So let's start with the moment equation. Pretty easy to solve. Add 123.75 to both sides and divide it by 9. And that makes FHI a positive 13.75 kips. Now it came out positive, and that means something important to us in method of sections problems. The way we draw our free body diagrams in method of sections problems, we always assume tension. If that assumption's right, the answer comes out positive. So a positive answer means tension in method of sections. So 13.75, remember HI is in tension. Now I wouldn't go to the table and fill that in because we don't really want it in the table. It's not something we need in our final answer, but it's something nice to know. So I'm going to go back to our table here and just kind of write it underneath and say member HI carries 13.75 kips in tension, just in case I might need it later. And I certainly do need it in my set of equations, but I don't need it as a final answer right here. I might need it in my next step though, so I'll keep it around. The y direction equation we can solve by adding FCH sine of 60 to both sides, sine of 60.945 to both sides. If we divide both sides by the sine of 60.945, we have 8.25 divided by the sine of 60.945. That gives us 9.4377. So FCH is 9.4377 kips. Now that also came out positive, which means our answer is in the right direction. So member CH is in tension. We assumed the right direction. The assumption was tension. So member CH, 9.4377 kips in tension. So that one we can go back to our table, since that is one of the ones we want for our final answer. And if there were constraints on the on the number of significant figures, we'd round that off. I'm just going to keep the full 5 sig figs in here. I'll assume we were asked for 3 sig figs in our final answer. So FCH carries 9.4377 kips in tension. So we've either got our final answer there, or we've got our final answer up to rounding to our final number of sig figs, depending on the specification of the problem. If nothing's said in the problem about how many sig figs, then just leave it like that. If nothing's said, more digits are better than fewer. So we've got that one. Now we can go back and find FCD. So we can plug in what we know. FHI is 13.25 kips. Sorry, 13.75 kips. FCH is 9.4377. Then we have the cosine of 60.945 degrees, and that equals 0. So you might be suspecting here when we add all this up, we're going to end up with a negative answer, since all we see there is positives, and this has to add up to 0. So there's got to be something negative in there. If we calculate the 9.4377 cosine 60 term, 60.945, you get 4.5834 plus FCD plus 13.75 equals 0. And if we solve that, we'd add our 13.75 in, and that gives us 18.333 kips negative. So to have this add up to 0, member CD, FCD, that symbol, has to be negative 18.333 kips. So the negative means that we've got compression. The assumption in method of sections is always tension. So when we get something that tells us we have a bad assumption, that means we've got compression. And that was one of the members we wanted. So we'll go back to the table and put that in. Remember, the loads are always positive. We use up the sign when we flag tension or compression. So don't write negative numbers in your load column. The load column is just how much force is it. The direction is taken into account there. The sign is taken into account. So member CD carries 18.333 kips compression. And that kind of makes sense looking at the structure. We learned that when we've got these gravitationally loaded structures, they tend to want to bend down, putting the top into compression and the bottom into tension. Cross members are harder to figure out, but the top is generally in compression, the bottom is generally in tension. And since member CD was in the top, we'd expect compression from that. So we've got everything we can from one cut. We got 3 unknowns. One of them we really didn't care about, so it's kind of tagging along for free. We now need to get member DH. Now there are a couple of approaches. If we want to stick with method of sections, we do another cut. And that other cut, see if I can get a different color to show up on the camera here. There we go. That other cut would be through this way. And it would be up to us whether we wanted to close that to the right, which involves a heck of a lot of forces, or close it to the left, which really only involves 2. So if I'm going to do it by method of sections, I'd probably close to the left, just because it seems like less work than closing to the right and dealing with those 3 forces. And then we'd get equations of equilibrium, but we have some of the values already known. So it's not going to be that bad of a set. We only really need one number, and if we're lucky, one equation will give us that answer. So let's see how we'd work that out, sticking with method of sections. So let's draw the part of the truss we're keeping. If I'm going to close to the left, then I have 2 of the bays fully enclosed. So I've got one bay, and that's one like that. We have another bay that looks like that. And then I'm cutting through. If I cut through CD, it'd be that there. If I cut through DH, that'll be up like that. And I cut through GH. So I have FGH. I have FDH. And then I have the force. If I draw it out just like I would any other method of sections problem, I draw it pulling out in tension as FCD. But we're going to have to be careful there. We'll come back to that in a second. And then I've got that 8 1/4 kips there. Don't forget the 10 kip force that's hanging right there at H. Forget that, that's definitely going to throw things off. So there's our free body diagram. I think I've got everything in that one. And we'll have the same angles involved. So we already know this angle is 60.945 degrees. Now let's look at how we'd use the information we've already got. Before we go and find equations, we've got FCD here, but we already know member CD carries 18.333 kips in compression. If we're going to set up our equations using the same technique we would if we didn't know what FCD is, we'd have to understand that to plug in a value for FCD, we'd have to plug in that value negative, because we're assuming here that member CD is in tension. It's a lot easier to draw with it pulled out and rather than pushing in and come up with our equations. We are probably best to stick with the methods that we're used to. So we could pretend that we don't know anything about CD, do this cut, and this might have been where you started. You might have done this cut first, but we'd do this cut and set up the equations, assuming we didn't know what FCD was. Then we'll plug in FCD, but where you'd have to be really careful is you can't just plug in 18.333. It's the same assumption we're making here in the previous cut. And when we did that assumption, we got a negative value for FCD. We'd have to use the symbolic value of FCD, which is negative 18.333. So it can get a little tricky reusing information from previous cuts. You got to make sure you get your signs right. So let's set up the equations and then we'll substitute in. And maybe if we're lucky, the equations will be set up that we don't even need FCD. We'll see how it goes. So let's do our sum of forces in the x direction. In the x direction, we've got a positive FCD. We're going to catch a piece of FDH to the right. That's going to be the adjacent piece, so it's cosine of 60.945 degrees plus FGH. And nothing else because there are no other forces in the x direction. If we do our sum of forces in the y direction, We've got a positive 8.25 kips. We've got a negative 10 kips. And then we've got a vertical piece of FDH. We've got FDH sine of 60.945 degrees. And that's all we've got in the y direction. And we could go ahead and get the moment equation too. We'd probably pick H for that, and that would give us a moment with FCD and with the 8.25. But if we look at what we've got right here in the y direction equation, we want DH. In the y direction equation, DH is the only moment, is the only unknown. So if we solve the y direction equation, we're done. So we didn't even really need to worry about FCD and how to use that from other parts of the problem. It turns out by making this cut, this slanted member is the only thing opposing the vertical forces. So we can figure out how much FDH has to be to keep this thing in vertical equilibrium. And we've finished the problem. So let's solve that. So we have 8.25 minus 10. And that gives us a negative 1.75 plus FDH sine of 60.945 degrees. That's 0. We'd add 1.75 to both sides. So we have FDH sine of 60.945 degrees. And that equals 1.75. Divide both sides by the sine of 60.945. And we'll get our final answer. Sine of 60.945. 1.75, 60.945 sine divide. And there we get a positive. So FDH is a positive 2.0019 kips. It came out positive, and in method of sections problems, when the answer comes out positive, we know we've got tension. So member DH carries 2.0019 kips in tension. So 2.0019 kips in tension, and we've got the problem solved. Now, it's not the only way to solve the problem. Maybe you didn't want to do another cut through the truss. Instead, you wanted to do a jump to method of joints. If you feel comfortable with both methods, using them together can be a very flexible way of approaching the problem. So as a way of reviewing method of joints and making sure we can see how to use it in a problem like this, let's get our final answer, at least that value for FDH, by doing method of joints. If we go to joint H, at joint H, we have 4 unknown forces, but from our first cut, we figured out 2 of them. So we've only got 2 unknowns. That's something that can be solved in method of joints. Remember, at method of joints, at each joint, we can only handle 2 unknowns because we've only got 2 equations. Sum of forces in the x direction and sum of forces in the y direction are both 0. We do have to, again, be careful about importing information to make sure we get the directions right, and remember our issues with direction in method of joints and how it's different than method of sections. So let's draw the free body diagram for H. So this is optional. This is if you're fine with the solution you've got so far and you're watching this on the video, feel free to skip ahead to our next problem. But if you're interested in seeing how you could use method of joints here and want to get a little review on that, keep on watching. So here at H, we've got 10 kips. We know that, so that's no problem with interpreting. We've got HI. We know HI. We learned HI through our first cut. It was 13.75 in tension. So if you have to go back to those pictures of what tension and compression look like, remember that in tension, the member is stretched out. So it's trying to shrink back to its original size. So in tension, the joints feel pulled toward each other. But in compression, the member is squished down and it's trying to expand back out. In compression, the joints are pushed away from each other. So we've got member HI over here to the left of joint H. So we're on this end of the beam. We've got tension. So joint H is going to feel pulled to the left with 13.75 kips. So we've got 13.75 kips to the left there. Member CH, we also know, member CH was 9.4377 in tension. Member CH is up to this side, upper left, so it's going to be pulling joint H to the upper left. So it'll look something like that, carrying 9.4377 kips. And we know that angle, the angle is 60.945 degrees. And that helps us figure out how to draw our remaining values. It makes sense that GH would be over here, and member DH would be over there with that same angle, 60.945 degrees. So a little bit of a complex free body diagram there, but not something that we should have much difficulty handling. Now, with a little bit of practice, you might be able to see into the equations a little bit and say, well, I've done enough of these that I know that if I do my x direction equation here, I'm going to end up with two unknowns in it, which is generally fine, but I only really want one of these unknowns. If I do my y direction equation, GH isn't going to show up, only DH is, and a couple other forces. So I'm just going to do the y direction equation here. If I really wanted to know GH, I'd have to do the whole thing, but y direction equation is all we need. So let's do the sum of forces in the y direction. I've got a negative 10 kips. I've got a piece of this 9.4377. I've got the vertical piece of that, and that's the opposite side, so that is sine. So I have a positive 9.4377 kips, sine of 60.945. And then I have the vertical piece of FDH, so that would be FDH sine of 60.945 degrees, and that equals 0. No other vertical forces, so just three terms. 9.4377 sine of 60.945 gives us 8.25. So minus 10 plus 8.25 plus FDH sine of 60.945 degrees. Well, that ought to sound kind of familiar. It's the same y direction equation we got in the second cut, trying to solve it by method of sections. Almost the same anyway. Well, no, exactly the same. We have a positive 8.25, we have a negative 10, and then we have FDH sine of 60.945. There's a negative 10, there's a positive 8.25, there's FDH sine of 60.945. So when we solve this, we're going to get exactly the same answer. FDH is 2.0019 kips. It came out positive, so the direction we've assumed here is correct. Member DH is over here like that. That looks like the end of a beam in tension, or end of a member in tension. So again, member DH, we get 2.0019 kips in tension. So either approach is acceptable, and I'd take either as a homework solution. I wouldn't hold you to using only method of sections in that problem, as long as you used it once to get something. What I was trying to avoid, I think, when I wrote that question, was people trying to just use method of section or method of joints to solve the whole problem. But as long as you use method of sections once, you've met the objective there of that problem, and then you could jump into method of joints to finish it up. Either way works. Any questions on that one?
Nope.
All right. So there we go. So let's go back to the notes. A little bit long on the homework there, but it's a good problem, good review, and more practice we can do, the better. So let's go back to the notes. And today we're just going to practice on frames. So let's take a look at a frame example. I've got one set up for us here. I don't have it in the notes, but I'll draw it up. So here we're going to kind of do a crane example. So we'll have this primarily vertical structure. Looks something like that. It's going to be supported on the ground by a pinned support. It's going to have a boom that goes off on it. So there's going to be a boom that kind of goes off to the side here. And there'd be a pin here. Now, if I hang a weight on this boom, it's going to try to tilt everything to the right. So I've got to put some other support over here. And what I'm going to put here is some wall that's suspended by something with a roller holding on to it. And let's see, then of course, if I put a load on this crane, it's going to want to fold this thing up. So I'm going to need some sort of cross member. Something like that. So we'll have A, B, C, and D, and then we'll have E there, and we'll put, say, 5 kips on that. And we'll make this thing, let's see, we'll go 4 feet here, maybe 6 feet there, and another 2 feet there. And then we'll do, let's say, here over to E, we'll go 8 feet, and then another 2. So the scale's a little bit off there, but it'll work out. So there we've got 8 feet, 2 feet. We'll relabel joint E because I drew right through it. So there we go. And just like every other problem, not a bad idea to look at it and convince yourself, or try to look at it and say, do I believe this is in equilibrium? And I think I can believe this is in equilibrium. When this thing pulls down, it's going to try to rotate to the right. This roller is going to stop it. This is going to try to kick off to the left. That pin's going to stop it. The horizontal member is going to try to rotate, but this BE is going to stop it. So I can see how this could be worked out in equilibrium. Now, if we count up our unknowns here, we have, looks like a total of 9 unknowns. So we've got, for each of our pins, we have 2 unknowns. The X and the Y direction reactions at each pin. For a roller, we only have 1 unknown, since a roller reacts perpendicular to the surface that it's supported on. So we'd expect a horizontal unknown here, an X direction unknown. A is another pinned support or a hinged support, so I'd expect 2 unknowns there. So in our table, for our answers here, we'll have our columns here, our X forces and Y forces, and these would all be in kips. And our magnitude for our final answer, where the magnitude, remember, is the square root of the X force plus the Y force. Our joint, we've got 5 joints total, or 5 points of interest, I suppose. Not all of them really are joints. We've got A, which would definitely have an X and a Y. B, C, and E would all have X and Y components. D is a roller. So D only has an X direction, no Y direction. So I'm going to cross out the Y space here for that. And that's where my 9 unknowns come from. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. And with 9 unknowns, I need to have 3 sets of 3 equations. So that means I'm going to need to do 3 setups in this problem, 3 free body diagrams. Now, one approach would be to just use each of the 3 members. I could draw the free body diagram of member AD. I could draw the free body diagram of member CE. And I could draw the free body diagram of member BE. All of those would work. Each one would give me 3 equations. But if I went that way, I'd probably have a lot of equations to deal with and not a lot of numbers filled in the table. We can also treat the whole structure as one object, do the external problem. And the way the structure is supported externally with a pin and a roller, that's 3 unknowns. So if I do the free body diagram of the whole structure and solve the equilibrium for that, the external problem, I'm going to get 3 numbers right away that I can fill into my table. And that's probably going to make things easier when I go and do my other setups, the other 2 setups I need to get all of my unknowns. So I think that sounds like a pretty good way to go. So let's do that. Let's first draw the free body diagram of our whole structure. And I'm going to simplify the structure just by drawing lines instead of the fully dimensioned members. So we've got a vertical here like that. We've got a horizontal. We've got a cross piece. Up at the top, I've got a roller. And so a roller exerts a force perpendicular to the surface that it's on. So I'll call that RDX. Down at the bottom, we had that pin. So, and I'm not really clear on exactly what directions the forces are going to be in. So I'll guess RAY and RAX. And then we have the only external force applied. We've got that 5 kips right there. And I'll copy the geometry as I need it from the other problem, or from the drawing. So there are all the forces we've got, just 4 external forces. 1, 2, 3, and 4. Everything else is an internal force. Well, we've got 3 equations we can build out of this. Sum of forces in the x direction and y direction are 0, and sum of moments are 0. So we've got moment there. So sum of forces in the x direction. Well, we've got a positive RAX and a negative RDX. So no help so far, no numbers yet. Sum of forces in the y direction. We've got a positive RAY and we've got a negative 5. Well, hey, we ought to get a number out of that one. That one, hopefully you can solve right away and just say, well, obviously then RAY is a positive 5 kips. So we've got something already we can fill in our table. The y component of A is 5 kips. And then we need moments, and I think A is going to be a perfectly fine point to pick for our moments. So sum of moments about A, that's going to knock out RAX and RAY, but both the 5 kip force and RDX are going to have moments. So 2 terms in our moment equation. RDX is 12 feet away from RAY. We can see that here, 4 feet plus 6 feet plus 2 feet. So our arm for the RDX force is 12. So we have 12 RDX. Pinned at A, pushing to the left, going to be a counterclockwise moment. So it's positive 12 RDX. And then the 5 kip force, its line of action here is 10 feet away from A. So this line of action is 10 feet away from A. So our arm is 10 feet, force is 5, so we have 50. Pinned at A, pulling down, that's clockwise, so negative. So 12 RDX minus 50 equals 0. That's going to let us solve for RDX. RDX is 50 divided by 12. That's 4.1667. So 4.1667 kips. So another value we can plug into our table. It also came out positive, so we know our direction's good. So 4.1, oops, RDX, 4.1667. Then we need RAX. Well, from our x direction equation, it says RAX minus RDX is 0. Well, that only happens when those two values are the same. So RAX and RDX have the same value, so I shouldn't have scribbled that out, I suppose. 4.1667. So a little bit sloppy on my part there, but we can see it there, 4.1667 kips. So now we've got 3 numbers, and that's all we can get out of the external problem. So best case scenario, 3 equations, 3 numbers. So we've got 3 out of 9 of our unknowns. We're a third of the way done. We need another setup. So last time I gave the advice to avoid working with slanted members. Slanted members usually give you more equations than unknowns because of the way that the moments work. You end up getting more equations than unknowns. Sometimes you can't avoid working with one of the slanted members, but other times you can. And I think in our practicum problem tonight, maybe we'll do a problem where we can't avoid working with a slanted member. So we'll see what we can do on that, but I see how to work it because you have a homework problem on the bonus homework that involves having to work with a slanted member. So it'd be useful if we could see it working once in class. Always going to be easier to work with vertical or horizontal. And I'm going to work with the horizontal first here. So let's draw the free body diagram of the horizontal member. Now, the technique that I use to keep my signs straight in working with these problems is to make sure that the first time I draw forces for a joint, I always draw them positive. The second time I use that joint, the second time I see that joint show up in a free body diagram, I draw the forces negative. That makes sure I'm taking into account Newton's second law and avoid sign errors, because the forces that one member feels from another are going to be equal and opposite. So for member CE, I've got this horizontal member. I've got joint C here and joint E here. There's no doubt about the 5 kip force. It's right there. But since I've never used joint C before in any free body diagram, and I've never used joint E before in any free body diagram, I'm going to assume both the forces that I get from those are positive. So I have RCX and RCY. I'm going to have REX and REY. Well, this is a non-concurrent force system, so I can use the same equilibrium. Sum of forces in the x and y direction are 0, and sum of moments about a point, 0. So in the x direction, I have a positive RCX and a positive REX and nothing else. So that sum is going to be 0. Sum of forces in the y direction, I've got a positive RCY, a positive REY, minus 5. So nothing's looking good so far. I can't get any numbers so far. Hopefully the moment equation will work well for me. And I'm going to pick joint C as my pivot point. If I pick joint C as my pivot point, it's going to knock out RCX and RCY. It's also going to knock out REX because REX has a horizontal line of action right through C. So just two terms, REY and the 5 kips. Now measured from C, part of the reason I picked C here is because I've got measurements from it. From C to E is 8 feet. So REY has an arm of 8 feet. So it's 8 REY. Pinned at C up would be a counterclockwise moment. So it's positive. And then I've got the 5 kips. 5 kips is 10 feet away from C. So that's 50. And because we're pinning at C and pulling down, that would be clockwise. So negative. All right, so at the very least, it looks like I'm going to be able to get REY out of this. And once I get REY, I'm going to be able to find RCY. But that's where it's going to end. So I'm going to get 2 numbers out of this and 1 equation that I'm going to have to wait till later to use. So let's solve it out here. 8 REY equals 50. We divide 50 by 8. We get 6 1/4. So REY is 6.25 kips. So we can fill that in our table. REY is 6.25 kips. Now that we know that, we can go up here and replace REY with 6.25. That'll make RCY minus 1.25 equal to 0. Sorry, plus, jumping ahead in my head here. 6.25 minus 5 is a positive 1.25. RCY plus 1.25 equals 0. Therefore, RCY must be a negative 1.25. And that's kips. Now, signs really don't matter all that much with respect to these kinds of problems, but we do have to track them because we can't interpret sign anymore as meaning tension or compression, since these members might be bending and twisting and all of that. So we'd go right to the table. This is the only place where we put negatives in the table. RCY, so RCY is negative 1.25 kips. It won't make any difference for our magnitude since when we square, the signs go away. But that's the best I can really do out of this free body diagram. So I got 2 numbers, but I left over with this 1 equation, which I could have expected because I had 4 unknowns. 4 unknowns, worst case, I get 3 equations and I have no unknowns. I can't solve for anything. Best situation I can hope for is what we got. 3 equations, but 2 of them I could solve. 1 of them I'll have to wait till later. So that RCX plus REX equals 0. I'm going to put off to the side here. RCX plus REX equals 0 as a constraint that must be in the system. And that'll help me later on when somewhere along the line I'm going to find RCX or I'm going to find REX. And that means I'll be able to find the other one. So that's all we can get out of the horizontal. And now we've got, out of our 9 unknowns, we have 1, 2, 3, 4, 5 of them plus 1 equation. So it's really 6 pieces of information, which is exactly what we'd expect after doing 2 free body diagrams at 3 equations apiece. But that's all I can get out of the horizontal member. So next we'll do the vertical member. The vertical member will set up the free body diagram. It's a little noisy. There's a lot of stuff there, but we can make it work. For the horizontal member, up at the top, we've got RDX, and RDX was 4.1667 to the left. So 4.1667 kips. We have joint C, which we'll have to take care of. We have joint B, which we'll have to take care of. And then at A, we already know what's going on. At A, we had a 4.1667 kips to the right. And 5 kips up. So we have C and B. Now, joint B, I haven't used before. I haven't encountered B before. I have not drawn anything about it in a free body diagram anywhere. So that means draw it positive. RBX and RBY. C, however, I've used before. I've already made an assumption about C. In my free body diagram for the horizontal member, I assumed RCX was to the right and RCY was up. To stay consistent with Newton's third law, I have to reverse those directions because what the horizontal member feels at C due to the rest of the truss, due to that vertical member, is going to be in the opposite direction of what the vertical member feels from the horizontal one. It's equal and opposite reactions. So to keep that consistent and make sure I can use the equations interchangeably without getting sign errors, I'm going to draw RCX and RCY. So that's just taking into account Newton's third law. Well, there are a lot of arrows on that drawing, but it'll get a little simpler when we do our sums. If we take our sum of forces in the x direction, we have a negative 4.1667. We have a negative RCX. We have a positive RBX and a positive 4.1667. So those are all the x direction forces. 1, 2, 3, 4. Got them all. Well, look at what we're doing here with the 4.1667s. They're equal and opposite. Negative plus a positive. So they cancel each other out. And all I'm left with is negative RCX plus RBX equals 0. So that's the equation I get in the x direction. So not as bad as it looked initially. Let's do our sum of forces in the y direction. In the y direction, I've got a positive 5. I've got a positive RBY. And I've got a negative RCY. Not really much I can do with that equation except subtract 5 from both sides and get RBY minus RCY equals a negative 5. So far, not a lot of help from these equations. We can't really solve either of these two just yet. Maybe we can if we look back at the table and pull in some information. We'd need something at C. We've got CY, so it looks like we'll be able to get something out of that. So it doesn't look too bad. But now we need our moment equation. We're definitely going to need that moment equation. And we've got to be careful about picking our pivot point. Joint C or joint B should be the only ones we consider. If we pick any other point, we're going to knock out everything except 2 unknowns. If we pick C or B, we're going to knock out everything except 1 unknown. So I think just for simplicity here, I'm going to pick joint C. So I'll take joint C, which means no moment from RCY, no moment from RCX, no moment from RBY because the line of action of RBY goes through C, no moment from the 5 kips, same reason, but I'm going to get a moment from the 4.1667 kips up at the top, and I'm definitely going to get a moment from the 4.1667 kips down at the bottom, and I'm going to get a moment from RBX. So I'll have 3 terms. To figure it out here, we're going to have RBX. I got to have the arm for that. The arm for that is the distance from C. That's 6 feet. So we have 6 RBX. pinned at C pulling to the right, that's counterclockwise, so it's positive. The 4.1667 at the top is 2 feet away. So we have 2 times 4.1667, which is 8.3334. So we have 8.3334. Pinned at C pulling to the left, that's also counterclockwise, so it's positive. And then we have the 4.1667 down at the bottom. That is 10 feet away from C. So we have 10 times 4.1667, so that's 41.667. And pinned at C, pushing to the right, counterclockwise, so it's positive. So it looks like we'll be able to solve the moment equation right away. 8.3334 plus 41.667 is 50.000, so it's 50. We have 6 RBX plus 50 equals 0. Subtract 50 from both sides, so 6 RBX equals a negative 50, and divide by 6. And we get RBX is a negative 8.3334 kips. So that's my value for RBX. So we can fill that into the table. RBX is negative 8.3334 kips. Knowing RBX, we can now go back into our x direction equation. If RBX is negative 8.3333 kips, and that equals 0, got to work out the negatives here, but if we add to both sides, we get negative RCX equals positive 8.3334. Negative RCX is a positive number, so RCX must be a negative number. RCX is negative 8.3334. So RCX, negative 8.3334. We can now use our equation here. RCX was negative 8.3334. We got to add something to that to get 0, so REX must be a positive 8.3334. And then just one value left to get, RCY, or an RBY. RCY, we know what that is. It's negative 1.25. So be careful with signs here. RBY minus negative 1.25. The value RCY is negative. So we've got to deal with that double negative. That's equal to negative 5. Double negative is a positive. And when we subtract 1.25 from both sides, RBY equals negative 6.25 kips. So negative 6.25 for RBY. So negative 6.25 kips. So there we go. We've got our table filled in. We figured out the equations. And now the last thing to do is find our magnitudes. So we use the Pythagorean theorem. We'll take for A, 4.1667 squared plus 5 squared square root. And we get 6.5086. For B, if you look at the values for E, B and E should come out the same, because even though we've got negatives here and positives here, the magnitudes are going to be the same, because when we square negatives, we get positives. And that, if we look at that, that seems kind of strange at first, but if you look at the member, it's a two-force member. So it's definitely got to have the same forces at both ends. That's what's needed to line up the force with the member. So two force members, whenever there are no other forces acting on the member except at the ends, you'll always get that value. You'll always get that behavior. You'll get the same exact values up to a sign. So we've got 8.3334 squared and 6.25 squared added together, square root, we've got 10.417. So 10.417 and 10.417. For anything with just one component, the magnitude is the value of that one component without any sign, so 4.1667. And then we've just got the last one at C here, 8.3334 squared plus 1.25 squared added square root. And that's 8.4266. Now, if the problem spec'd fewer significant figures, then we just round down to those. But there we go. That's another method of joints problem. Frame problem. So another frame problem, magnitudes at the joints. Any questions there?
Nope.
All right. So we're going to pause for a quick break, and we'll come up with another problem for our practicum session. All right, so here's our practicum problem for tonight. So like I promised, one that we need to deal with a slanted member on. It's really not all that bad for the most part. It's just it's not as clean usually as dealing with a horizontal or vertical member. But it turns out this one's not too bad. So in this case, we have to deal with a slanted member because that's all we've got. So this is some structure hung from a ceiling, and it would be a truss, except for the fact that we're loading up the beams in the middle. So horizontally, that 200-pound force is 2 feet away from A, and vertically, it's 2 feet away from A. And the 6-foot force horizontally is 3 feet from B. So that's in the middle of the member. Can't load a truss like that, but we can load a frame that way. So if we look at the number of joints we've got 3 joints. We get 2 unknowns from each joint. So we're going to have a total of 6 unknowns here. So we can start our table. And the problem specifying 3 sig figs for our final answer. And that really only applies to the magnitudes because it's asking us for the magnitude. So we can just round in our last step when we calculate our magnitudes if necessary. So we'll have 4 columns there. X and Y and the magnitude will all be in pounds. And we've got joints A, joints B, and joint C. So A, B, and C. So 6 total unknowns, 1, 2, 3, 4, 5, and 6. And the magnitudes don't count as unknowns because once we know the components, we can find the magnitudes. So we've got 6 unknowns. That means we're going to have to do 2 setups. We're going to have to do 2 free body diagrams and 2 sets of equations, since we get 3 from each. So let's start with the external problem. So we've got pinned supports up here at A and B. And then we've got another pin at C. So let's do the external problem of something that looks sort of like this. We'll have RAX and RAY. We'll have RBX and RBY. Then we've got our loads right at the middle of member BC. We've got 400 pounds pulling down. And then at middle of AC, we've got 200 pounds pulling down. And we'll figure out the geometry as we work through the problem. So let's do our sums. Coordinate system, X to the right and Y up positive, counterclockwise moments negative. So sum of forces in the X direction. In the X direction, we've got a positive RAX and a positive RBX and nothing else there, so that's equal to 0. Sum of forces in the Y direction, we've got a positive RAY, we've got a positive RBY, we've got a negative 200 and a negative 400. So that equals 0. No help so far as getting numbers. So maybe the moment equation will be able to help us out a little bit here. If we take our sum of moments about, I'm going to just arbitrarily pick point A. That's going to knock out RAX and RAY. And because it's a pretty safe assumption to assume the ceiling here is level, that it's also going to take out RBX. So we'll just have RBY, the 400-pound force, and the 200-pound force. So RBY, according to our drawing, is 10 feet away from A. So we have 10 RBY. If we're pinned at A and pulling up over here, that would be a counterclockwise moment, and those are positive. The 200-pound force, remember we need the distance between the pivot point and the line of action of the force. So to the pivot, from the pivot point to the line of action, that's half of this 4-foot distance, so that's 2 feet. So 2 feet, 200, that's 400 foot-pounds. Pulling down, pinning at A, that's clockwise, so it's negative. And then we've got the 400-pound force. The 400-pound force, its line of action is halfway through the 6-foot range. So that's 3 feet from C, but C is 4 feet from A. So 7 feet total. 7 times 4, 2,800. So we have a negative 2,800 foot-pounds. No other forces with moments. Well, the moment equation looks like we're going to be able to solve. So if we simplify that down, we've got 10 RBY minus 3,200 equals 0. And solving that, RBY is a positive 320 pounds. So we finally got a value we can plug in. RBY is 320 pounds. We can now go back to our y direction equation. RBY is 320. If we take 320 and subtract off 200, and we subtract off 400, we get negative 280 there. So RAY minus 280 equals 0. So RAY has got to equal 280 pounds. So RAY 280. So we've got 2 out of 6 unknowns down. Unfortunately, we don't have enough to do anything with RAX plus RBX equals 0. So we'll write that off to the side here. RAX plus RBX equals 0. So that'll be an equation in our equation bank. Well, that's all we can really get from the free body diagram of the whole structure. The external problem can't be solved any further than that. So let's go to one of the members. I'm going to use member AC for this. So member AC should be all I have to work out because there's only 3 more unknowns. Well, there's only total 6 unknowns. I've got 2 numbers and an equation. So I've got 3 pieces of information there. I only have 3 more unknowns. So one more setup's going to do it for me. The only question is, how complex is it going to be? Well, I've got joint C here. I've got this 200-pound force in the middle. And then I've got A. Now, A, we already know something about what's going on there. We know we've got 280 pounds pulling up at A. We don't know what RCX is, or RAY is, RAX is, excuse me, so we'll just leave it as RAX. Remember, the whole flipping Newton's third law thing only applies to internal joints, to joints where you are drawing 2 members free body diagrams. It doesn't count for the external problem and for working with the members there. So we can leave it the same way we assumed it in the initial problem. Now C, we've never seen before. Haven't used it in a free body diagram, so we'll assume positive, RCX and RCY. And we'll draw our coordinate system, X, Y, and counterclockwise moments, and we have 4 feet of height and 4 feet of width. So there's all the geometry we'll need. And if we look at it carefully, there are only 3 unknowns. 3 equations, 3 unknowns. No matter how bad the equations are, we should be able to get numbers out of this. So let's do our sum of forces in the x direction. Sum of forces in the x direction, we have a positive RAX. We have a positive RCX. Nothing else in the x direction. Take our sum of forces in the y direction, we've got positive 280. We've got a negative 200 and a positive RCY. Nothing else in the y direction, so that equals 0. And that's an equation that we'll be able to solve pretty easily. Let's simplify it a little. That's 80 plus RCY equals 0. And then we'll be able to solve that. RCY is a negative 80. So RCY is negative 80. So we've got another number we can fill in. So RCY, negative 80 pounds. Then we need our moment equation. Moments are what get a little bit challenging. You got to be really, really careful with them when you're dealing with slanted members. This one's not too bad because we don't have that many unknowns here. So if we had more unknowns, it would be a little bit harder, but you got to make sure you don't miss any moments. So I'm going to pick joint C here as my pivot point because it'll knock out my 2 unknowns. I don't really know RCX. I do have a value for RCY, but we could always, maybe I decided not to solve this equation in the middle here. And I'm going to wait till I have all my equations done. So I'm going to assume I don't know RCY here. So I'll pick C as my pivot point. All that ever knocks out in a slanted member is what's right at that joint. Everything else will have an arm, even horizontal forces and vertical forces, because they're some distance away and they're at an angle. But fortunately, the moments aren't hard to calculate as long as we know the geometry. We're going to end up with 3 terms in our moment equation here. We're going to pick up a moment from the 200-pound force. We're going to pick up a moment from RAX, and we're going to pick up a moment from 280. So 200 pounds, that's 2 feet away. The line of action here is 2 feet away from point C. So 2 times 200, that's 400. Pinning at C, pulling down, that would be a counterclockwise moment, so it's positive. RAX, horizontal here, RAX is 4 feet from RCX. The distance between the pivot point and the line of action of the force is the arm. So 4 times RAX. Pinned at C, pushing to the right, that's clockwise. So it's negative. And then we've got the 280-pound force. 280, its line of action's down here like this. That's 4 feet away from C. So it's 4 times 280. That's 1120. Pinned at C, pushing up there, that'd be a clockwise moment, so it's negative. So there we've got a moment equation we'll be able to solve. If we take the negative 1120 and combine it with the positive 400, we end up with a negative 720. So we have negative 4 RAX minus 720. If we add 720 to both sides, we have negative 4 RAX equals a positive 720. Divide both sides by negative 4, and RAX is a negative 180. So negative 180 pounds for RAX. So we can put that in our table. RAX, negative 180. Still two unknowns, BX and CX. Well, CX we can get from RAX plus RCX equals 0. RAX is negative 180. So negative 180 plus RCX equals 0. So RCX must equal positive 180. And then our final answer will come from the equation we couldn't use from our external problem. RAX is negative 180. So negative 180 plus RBX equals 0. So RBX must equal a positive 180. So there we've got our table almost filled in. We've got our 6 unknowns. To get our magnitudes, we square the x and y components, add them together, and take the square root. So 180 squared plus 280 squared. Added together, square root, that's 332.8687, rounded to 3 sig figs, because we haven't done any rounding yet, so we don't have to worry too much about that. But rounding to 3 sig figs, we've got 333 pounds for A. So that's the force that's trying to shear through A. If we knew something about the diameter of A, we could talk about the shear stress involved. And that's the part of the course we're going into next, looking at the materials and how much stress is involved and whether this thing could handle. This is a 1/4-inch nail, or this is a number 10 nail or something like that, a 6-weight or 6-penny nail, something like that. Is this going to handle that stress, or is it going to shear out? We have 180 squared and 320 squared. That's 367 rounded to 3 sig figs. And then we've got 180 and 80. So 197. So there we've got our final answers. So we'll frame the problem in there. There we go. Any questions there?
Nope.
All right. I think that's probably enough for the evening. We'll close out here. Next time, we will be doing just a problem session. So next time is practice on structural analysis. So any problem that you encounter in studying, or that you have an issue with, or that you had a problem with on homework, bring it up and we'll work through it. So any method of joints, method of sections, or frame problem. And as always, check last year's videos for some more example problems. I might have repeated some, I might have used different ones, but you can get some more example ones worked out if you get stuck. So that'll be next time. Any questions?
Nope.
All right. Well, have a good evening then.
Have a good weekend.
All right. See you Monday.